Let me welcome you to this lecture. We have now discussed some very important aspects of metal carbonyl chemistry. That is, we have looked at the electronic structure of metal carbonyl complexes, and we now understand the reason why carbon monoxide binds to metal centers through the carbon center but not through the oxygen atom. At the same time, we have also understood why only electron-rich metals or metals in low oxidation state form stable metal carbonyl complexes, and we have also seen how one can use the CO stretching vibration as a diagnostic tool to uh, understand the electronic nature or the pi acceptor ability of different pi acid ligands in different complexes. So let us now proceed further with this and discuss about the synthesis as well as some reactions of the metal carbonyl complexes. So to begin with, there are many methods of synthesis of these metal carbonyl compounds, but these reactions can be mainly categorized into three different type of reactions. That is, the first type of reaction that yields metal carbonyl complexes is the direct reaction of metallic powders, that is granular metallic powders, with uh, with carbon monoxide to give metal carbonyl complexes. So we'll see some examples of preparation of metal carbonyl complexes by following this direct reaction method, where it's not granular, it is finely divided metallic powder with carbon monoxide. And there are two important examples of metal carbonyl complexes which are prepared by this direct reaction of finely divided metallic powder with carbon monoxide. The first one is nickel, which reacts with carbon monoxide under 1 bar pressure and at room temperature, that is 25 degrees Celsius, to give us nickel tetracarbonyl. Now, another important metal carbonyl complex, that is iron pentacarbonyl, can also be prepared by this method, where you take finely divided iron powder and react it with carbon monoxide. But in this case, iron is much more reactive in metal as compared to nickel, and that is why the outer surface of these iron particles are generally coated with iron oxide, and that is why one needs to increase the pressure of carbon monoxide as well as the temperature to get iron pentacarbonyl, and 100 bar carbon monoxide pressure as well as 150 degrees Celsius temperature is required to get iron pentacarbonyl. Of course, if you take pure iron powder, then it will react with carbon monoxide at room temperature and at 1 bar pressure like nickel does. So anyway, this can be obtained from iron powder by following these conditions. So these are some of the metal carbonyl complexes that can be prepared by direct reaction of metal with carbon monoxide. We will now go and see the second method of preparation of metal carbonyl complexes, which is the most important method, as most of the metal carbonyls are prepared by following this particular method, where you reduce suitable metallic salts by using a reducing agent in presence of carbon monoxide gas. So reduction of metallic salts in presence of CO. That is the second method for preparation of metal carbonyl complexes. So when you reduce metallic salts from higher oxidation states to lower oxidation state by using a suitable reducing agent, the metal ions that are produced, or the low valent metal ions that are produced, react in situ with carbon monoxide to give us desired metal carbonyl complexes, and we will see some examples of this particular method. So one can prepare titanium hexacarbonyl starting from titanium tetrachloride. So this is coordinated to dimethoxyethane, which is taken as a solvent in this case, and one can reduce titanium tetrachloride from plus 4 oxidation state to lower oxidation state by using potassium metal, which is an alkali metal, and but potassium bare metal is highly reactive in nature, and that is why it is difficult to use bare potassium metal in the laboratory. So one uses, instead of potassium, the potassium naphthalene, where potassium metals are essentially coated by this naphthalene, which is a hydrocarbon, and the reaction is done in presence of 15 crown 5, which is a complexing, it's a crown ether actually, and can form complexes with potassium ions that are going to be produced during this reaction. And when in presence of carbon monoxide, so you add carbon monoxide also to this reaction, that is 6 equivalent of carbon monoxide, 6 equivalent of this, and 4 equivalent of the 4 crown 5 with 1 equivalent of this titanium Cl4 will give you so this sort of potassium crown complexes are formed. This is positively charged, and TiCO6, this is W negative, so you need 2 of these positive countercation complex ion, and this will come out of the potassium now. So you will have 6, and 4 of the potassium will form KCl. So this is how the reaction proceeds and gives us titanium hexacarbonyl 2 negative after reduction of TiCl4 by the potassium metal over here. So one can also use the less reactive, less violent container of potassium, that is sodium, as the reducing agent to reduce certain metallic salts, and then react the same with carbon monoxide to result metal carbonyl complexes. We will see one example where VCl3 is reduced by sodium in presence of carbon monoxide, and you need to do the reaction in solvent that is Alkyne, which is this dimethoxyethyl ether, and the structure of this is this, and it can coordinate to sodium ions that are going to be formed during this reaction in this fashion. So this will result eventually Na dialkyne 2. So sodium is essentially 6 coordinated, as 2 of these dialkyne ligand is coordinated to sodium, and this is positively charged, and sodium ions are present because after a reduction of vanadium from plus 2 oxidation state, here sodium goes to plus 1 oxidation state, and this is negatively charged in this way. So after this, what you can do is you can oxidize the carbonylate anion here by H3PO4 to give us neutral vanadium hexacarbonyl, which is a 7th electron complex. So one can, apart from this alkali metal ions, one can also use aluminium as a reducing agent. That is, aluminium metal itself can be used as a reducing agent to reduce certain metallic salts and thereby produce metal carbonyl complexes. So if you start with CrCl3, this can be reduced by aluminium, and in presence of CO, the reaction is done in benzene with AlCl3 as the catalyst, and it results chromium hexacarbonyl and aluminum chloride as the byproduct in this way. So this is how one can use aluminum as the reducing agent. We can also use alkyne aluminiums, which are very important reagents in organometallic chemistry, to reduce certain metallic salts again and then produce carbonyl complexes of those metal salts. So if you start with WCl6, then triethyl aluminium can reduce the tungsten from classic oxidation state to zero oxidation state, and if you do the reaction in presence of CO, the two equivalent of this, then WCO6 is produced and two equivalent of AlCl3, while the ethyl groups over here will undergo oxidative coupling to form C4H10, and that is going to be three equivalents of C4H10 is going to be produced during this reaction. So this is how we can use alkyne aluminiums as reducing agents to reduce metallic salts and thus react the low valent metal ions that are produced to react with carbon monoxide to result metal carbonyl complexes. Apart from this, carbon monoxide itself can be used as a reducing agent to reduce metallic salts or metallic compounds into lower oxidation state and thereby form metal carbonyl complexes. So example of this is you can take rhenium oxide when rhenium is in class 7 oxidation state and react the same with carbon monoxide, then it will result Re2CO10, and now rhenium from plus 7 oxidation state to 0 oxidation state is reduced, and carbon monoxide, which has reduced rhenium, will also get oxidized, so it will form carbon dioxide. So you need 17 equivalent of carbon monoxide, 10 equivalent forms metal carbonyl complex, that is Re2CO10, and 7 equivalent of carbon monoxide gets oxidized into carbon dioxide, while it is reducing the rhenium plus 7 to 0 oxidation state. So this is how carbon monoxide acts as a reagent as well as a reducing agent to form Re2CO10. We can also use hydrogen, which is a common reducing agent, to reduce metallic salts and then produce metal carbonyl complexes. So you can take cobalt carbonate and do reaction with hydrogen in presence of carbon monoxide to give us CO2, CO8, and 2 CO2 and 2 H2O. So you need 8 equivalent of this and 2 equivalent of this, and this is how we can produce. The carbon dioxide that is produced here is from the carbonate ion. Actually, it is not from carbon monoxide. Entire carbon monoxide is reacting with cobalt 0 to form CO2, CO8, while hydrogen is the reducing agent here to reduce cobalt from plus 2 oxidation state to 0 oxidation state in this case. So this is how we can use hydrogen as the reducing agent. So we have now seen several examples of where metallic salts are reduced in presence of carbon monoxide to form corresponding or desired metal carbonyl complexes. So the third method of preparation of metal carbonyl complexes involves thermolysis or photolysis of other metal carbonyl complexes. As such, metal carbonyl complexes are some of these metal carbonyl complexes are unstable towards heat or photoirradiation, and that is how one can prepare other metal carbonyl complexes starting from some metal carbonyl compounds, that is like thermolysis, by their thermolysis or by photolysis. So the third method is essentially thermolysis or photolysis of precursor metal carbonyl complexes. So you need to start with a metal carbonyl compound which is susceptible to either temperature or to light irradiation, and one example we will see iron pentacarbonyl, which is stable at room temperature but is susceptible to temperature or to light irradiation. It undergoes decomposition, and if you do photoirradiation in presence of acetic acid, then it produces Fe2CO9. So this is how one can prepare metal carbonyl compound starting from a precursor metal carbonyl complex, and by doing photolysis of the same. Here we have seen how one can prepare Fe2CO9 by following this method. So we have now seen all the methods of preparation of metal carbonyl complexes, and then we have essentially seen three methods of preparation. Now we'll go on and see the kind of reactions that metal carbonyl complexes undergo, or the reactivity of metal carbonyl complexes. Now, as such, the metal carbonyl chemistry is very well developed, and it has been going on for several decades. We already know that the first metal carbonyl compound was prepared way back in 1864 and 68, and since then a lot of compounds have been prepared, and their reactions have been already studied very well. So vast number of reactions are already reported for metal carbonyl complexes. So but during this course or during this lecture, we will not be discussing all the reactions, as they are beyond the scope of this course, and it is also beyond my capability, and we will stick to only few reactions which are important from our perspective as well as from the perspective of metal carbonyl chemistry. So we will start with one type of reaction that metal carbonyl compounds undergo, that is the substitution reaction. Now one can substitute some of these carbonyl ligands in a metal carbonyl complex by other suitable ligand. This L, one can produce N-X and NX. That is, we can substitute some of these carbonyl ligands, but not all of the carbonyl ligands. So X is generally is typically lower than N, and N is this is we will not be able to substitute all the carbonyl ligands for sure, and the different ligands which can be used to substitute the carbonyl ligand in metal carbonyl complexes are Lewis bases. One can use different Lewis bases. Then we can also use olefins, are very commonly used to substitute carbonyl ligands in metal carbonyl complexes, as well as we can also use arenes, different arenes for substitution of carbonyl ligand in metal carbonyl complexes. So these kind of ligands can be used for substitution of metal carbonyl complexes. Now these reactions, essentially the substitution reaction of metal carbonyl complexes by other ligands, has evolved into a standard method of preparation of low valent metal complexes or low valent organometallic compounds, because carbonyl ligands form complexes typically with low valent metals, and that is why they serve as precursor for preparation of other low valent metal complexes or with different other ligands. and one can start with carbonyl complexes and then do substitution with the desired ligand to produce your complexes of your desired ligand with metals in low valent oxidation state. So that is how the substitution reaction has become a very important reaction in organometallic chemistry, because it serves as a tool to produce low valent metal complexes of different desired ligands. So now one very popularly or commonly used variation of this substitution reaction in metal carbonyl complexes involve intermediate introduction of a ligand which forms labile metal ligand bond, and then one can replace this ligand by other suitable ligands or other desired ligands to produce the final product. We will see examples of this technique or reaction. That is, you can start with CrCO6, and then if you do reflux CrCO6 in acetonitrile, then you replace some of these three of the carbonyl ligands by acetonitrile, which is a poor ligand as it forms a very weak metal ligand bond with chromium metal here, and that is why they can be easily replaced by other desired ligands. In this case, we can do reaction with cycloheptathione, and it will replace the acetonitrile ligands in this complex to produce so it's a eta 3 ligand, the cycloheptathione now, and 6 electron donor we can see. So this is a 18 electron complex, and we could prepare this reaction by substitution of the carbonyl ligands via this intermediate complex formed with acetonitrile, which is a ligand which forms labile metal ligand bonds, and that is why it can be easily replaced by our desired ligand. So this is a commonly used technique where one uses or one employs an intermediate introduction of a ligand which forms labile metal ligand bonds. This reaction proceeds via thermolysis, that is by the carbon monoxide ligands from here, from this complex, were replaced by thermal treatment. We also have examples where photochemical substitution reactions are carried out, can be carried out. So we'll see just one example where carbon monoxide is replaced photochemically, substituted photochemically. So this is cyclooctene ligand and olefin, and if you do reaction with chromium hexacarbonyl under light irradiation, then you replace one of the carbonyl ligand by cyclooctene ligand here. So, and now we can introduce our desired ligand L, which will replace the cyclooctane ligand, as this forms labile metal ligand bond with the chromium ligand over here, and can produce desired metal complexes with our desired ligand L over here. So again, what we have seen is that this intermediate complex serves as a metal carbonyl transfer reagent, because one can transfer this part of the metal carbonyl part to bind with our desired ligand to form a final product. So these sort of labile complexes are known, which can further react with other ligands to form desired carbonyl complexes with other ligands, or heteroleptic metal carbonyl complexes are known as metal carbonyl transfer agents. So one typically transfers agent. So one prepares the metal carbonyl transfer agents and then reacts them with their ligands to produce desired metal complexes. And other examples of such metal carbonyl transfer agents are THF, MoCO5. So when you reflux MoCO6 in THF, then you produce this transfer agent where one carbonyl ligand is replaced by the labile THF ligand. So similarly, we also have CH2Cl2 CrCO5. So you can start with CrCO6, do reflux of the same with dichloromethane, and then you produce this labile intermediate, which on further reaction with other ligands can produce our desired product. Similarly, for iron, cyclooctene to FeCO3, which can be produced photochemically from FeCO5, serves as a metal carbonyl transfer agent for iron formation of different low valent iron complexes. So this is what we see, that how one can use this variation where one introduces a ligand which forms labile metal ligand bond initially, and then react the same the labile complex with other ligands to produce desired metal complexes. So now what we will see is the mechanism of these substitution reaction, or how these substitution reaction happen in metal carbonyl complexes. So if you use a 18 valence electron species metal carbonyl compound, then the substitution reactions in those compounds proceeds via following a dissociative pathway. So initially you say take chromium hexacarbonyl, then first a CO ligand will be replaced by will be removed to produce a low coordinate chromium species. So this is 18 valence electron species, and the intermediate formed is 16 valence electron species, because we start from a 18 valence electron stable species and form a 16 valence electron species here. This particular step is very slow in typically, and then once it is formed, then it can react with our desired ligand to give us the product in this way. So the second step is going to be very fast as compared to the first step, which involves dissociation of this 18 valence electron species, while the second step produces a 18 valence electron species after addition of L, and that is why it is typically pretty fast. So this step is the rate determining step for the dissociative pathway. Now if we see another example, that is the substitution reaction in nickel tetracarbonyl, again it is also a 18 valence electron species, and will undergo substitution via dissociative pathway, and it gives us nickel tricarbonyl here. So that is 16 valence electron, and after the addition of the ligand, you will have the product, which is again 18 valence electron. Now what is observed is that the nickel tetracarbonyl undergoes substitution much faster as compared to chromium hexacarbonyl. Now if one looks at the bond dissociation energy between the metal and the carbonyl ligand in these complexes, then one finds is that the bond dissociation energy in this case, in case of the chromium, is, that is chromium CO bond is 155 kilojoule per mole, while the bond dissociation energy for the nickel is 105 kilojoule per mole. So what you see in this case of the chromium complex, the bond dissociation energy is much higher as compared to the nickel carbonyl bond dissociation energy, which is 105 kilojoule per mole, and the nickel complex undergo substitution faster as compared to carbonyl complex that we have already stated. So this observation essentially suggest that they proceed substitution reaction via a dissociative pathway, as the bond dissociation energy in this case is much higher, and therefore substitution here is slower, while in this case bond dissociation energy is smaller, and that is why substitution in nickel tetracarbonyl undergoes faster as compared to what you see for chromium hexacarbonyl. And this essentially established that both of these complexes undergo this substitution via the dissociative, by following the dissociative pathway. So one final observation that has been made regarding substitution reaction in different metal carbonyl complexes is that if you compare the rate of substitution in different metal carbonyl complexes formed by elements within one particular group of the periodic table, then what you will observe is that the central metal ion in all the cases undergo, or carbonyl complexes of the central metal ion undergo substitution much faster as compared to the other elements or other carbonyl complexes formed by the other elements within the same group. So if you say, for example, if you take chromium, molybdenum and tungsten carbonyl complexes, one will observe that the molybdenum complex undergoes substitution faster as compared to chromium or tungsten complex. Similarly, cobalt, rhodium and iridium carbonyl complexes also, if you compare the rate of substitution in these complexes, you will find rhodium carbonyl complexes undergo substitution faster. Similarly, if you take nickel, palladium and platinum also, again one finds that palladium carbonyl complexes undergo substitution faster as compared to nickel and platinum complexes. But the reason for this observation is not yet known and is still under investigation. So with this, we will conclude this lecture. What we have learned during this lecture is we have looked at some of the preparative methods or methods of preparation of metal carbonyl complexes, and we have seen how one can prepare by following 3 different methods. And we have also looked at substitution reaction in metal carbonyl compounds, and we have seen that one can do substitution by using either thermal methods or by photochemical methods. And also we have seen that for 18 valence electron species, substitution undergo is by following a dissociative pathway. So with this, I will conclude this lecture, and thank you very much